This video, part 2, isomers, is a continuation of our alkane and isomers video. In our previous video, we had gotten an introduction to organic chemistry. We talked about a class of compounds called hydrocarbons. And then amongst those hydrocarbons, we decided to take a look at our simplest class called the alkanes. In this particular video, we're going to proceed and take a look at different ways of representing organic compounds, different types of structures. We're going to take a look at situations in which we have the same molecular formula but different structures leading to different compounds, and we're going to determine how to draw those structures. So when carbons begin linking together to form our alkanes, anytime we have ones with more than 4 carbons, they can form either a straight chain or a branched chain structure. This can result in a single molecular formula representing more than one molecule with different structures. So we can see that here in this image. We've got C5H12. And we have a couple of possibilities. We could have all 5 carbons connected in a row with the 12 hydrogens filling up each carbon to form 4 bonds to give us our pentane or our straight chain structure. But if we look at our other 2 structures, we'll notice that in the 2-methylbutane, we've got carbons connected in a row. We've got 4 carbons connected in a row. And then we have our 5th carbon as a branch. If we were to count all of our carbons, we still have 5 carbons. If we counted all of our hydrogens, we still have 12 hydrogens. So this 2-methylbutane has the same molecular formula, but we have this different structure. And because we have one of our carbons coming off as a branch, this is going to be called a branched chain structure. Now with our 2,2-dimethylpropane, we see the same thing. We've got carbons here connected in a row, and then we have carbons 4 and 5 as branches. We still have 5 carbons, we still have 12 hydrogens. So in this particular case, we've got 3 different structures that have the same molecular formula, but we have 3 different structures. And notice that each of these structures has different names because they are indeed 3 different compounds. So based on the example that we just looked at, where some structures are labeled as straight chained and others as branches, how can we define these structures, straight chain versus branch chains, based on the connections of carbons? So we've already talked about that a little bit. If I've got a straight chain structure, what we're looking at is having all of our carbons connected in a row. Whereas our branch chain structures have 1 or more carbons branching off of a chain. Now, to call a structure straight is misleading because these are 3-dimensional structures. Remember, each carbon actually gets that tetrahedral arrangement. So it's not really straight across. We're actually going to have more of a zigzag to our structure. But the point is that the carbons are connected in a row in the straight chain, and we've got carbons branching off in our branch chains. So different structures are going to result in different substances with different properties. If a molecular formula, such as our C5H12, can represent more than one structure, and therefore more than one compound, is a molecular formula very accurate in indicating the identity of the compound? So if we think about what we just saw, again, we had 3 different structures representing the same molecular formula, C5H12. If I just said C5H12, that could be referring to any one of those 3 structures, which tells me C5H12 tells me absolutely nothing. So that molecular formula is not very accurate in indicating the identity of the compound. All it does is tell me my total carbons and my total hydrogens. What we're going to find is going to be more accurate is something that gives us an indication of how those atoms are arranged. So our structural formulas are going to be far more accurate, and these are going to be the formulas we're going to use throughout organic chemistry to describe our structures or our compounds so that we know which substance we are talking about. So we've just seen structures with the same molecular formula. These are going to be referred to as isomers. Isomers share the same molecular formula but have different structures. And therefore, they're going to have different chemical and physical properties. So they are different materials. Because a given molecular formula can represent a number of isomers, it is more common to represent organic molecules using structural formulas. There are several types of structural formulas we can encounter. We have our expanded structural formulas. These are more representative of our Lewis structures. So if you recall Lewis structures from first semester chemistry, where you're drawing all of your atoms out, all of your bonds, all of your lone pairs, those are going to be our expanded structural formulas for organic compounds. Then we have condensed structural formulas, and then we're going to have line formulas or carbon skeleton formulas. Now, in your textbook, you're also going to encounter a structure type called a Kekulé structure. These are very similar to your Lewis structure, so they're that expanded structure. The only difference is they're going to omit lone pairs. So we're going to commonly see lone pairs on our oxygens or nitrogens. Those are going to be omitted if it's a Kekulé structure. So we want to talk the differences between each type of formula. So here in this image, we've got an expanded structural formula. So the expanded structural formula, if we notice here, it shows all atoms and all bonds. So the structural formula is going to give us an idea of how our atoms are arranged. They're going to represent that arrangement and structure. But the expanded formula specifically shows all atoms and all bonds. Now, we also had our condensed formula. Condensed formulas, which we're not seeing an example of here, but we can look at an example. A condensed formula, it's going to omit the lines for our bonds. So an example here, we would have this first grouping, CH3. This next grouping, I've got one carbon and two hydrogens, so we would have a CH2. CH2. And then CH3. So in that condensed formula, it tells us the same information. We know we've got these 4 carbons. We know we've got our number of hydrogens. It's showing us they're all connected in a row. So it's giving us the same information. It's just condensing it. It's omitting our lines. And then our final formula type was our line formula or our skeleton formula. With the line formula, it's going to omit atoms. Lines are going to represent bonds between carbons. These are more drawn in kind of a zigzag structure. So each point on the line is a carbon. We omit our hydrogens. If we have other atoms, such as an oxygen or nitrogen or sulfur, we're going to see those drawn and lines to them. But in our basic structure, we're going to omit those lines. So for this formula, we've got 1, 2, 3, 4 carbons. So its line formula is going to be a zigzag with 1, 2, 3, 4 points. So that's going to be my line formula. So in order to be able to represent the array of different compounds that can represent the same molecular formula, we've got to be able to draw the different isomers. When we're drawing an isomer, the first thing we're always going to do is we're going to draw a straight chain structure first. This will always give us our first isomer. Then what we're going to do is we're going to pull a CH3 group off the end. Now we're going to walk through this so we can see how each of this happens. But the first thing we would do is we pull a CH3 group off of the end. What this does is it drops us down to a smaller carbon chain. Now, we have to have the same numbers of carbons and hydrogens always. So what happens is that CH3 group we pulled off the end, it becomes a branch. And we're going to place it on an interior carbon. And it always has to be an interior carbon. That is going to give us our second isomer. Now, if we have multiple interior carbons, what we're going to then do is we're going to move that CH3 group down the chain. We're going to place it on each of those different interior carbons until we can no longer draw new structures. Now we have to be careful here because in reality, an organic molecule, it can bend, it can twist, it can fold, it can rotate, it can turn around. And so we may think we're drawing a different structure, but we're not actually. So there's going to be a couple of things we're going to do to ensure we are getting new structures. So to tell if we're drawing repeat structures versus new structures, the biggest key is always to number your chain. The biggest key with anything with dealing with organic compounds is to number your chains. So what that means is we're going to count our carbons. We will always count carbons. Now what we're going to do is we're going to number the chain from the end closest to a branch. And we're going to number our longest continuous chain. Once we've moved that branch around, drawing as many structures as we can, the next thing we do is we pull off a second CH3 group off the end. That now gives us 2 carbons to work with in branches. And we have a couple of varieties we could do here. One branch could just be a CH3 group, or we could have 2 CH3 branches. The other option is our branch itself could have multiple carbons. So we could have a CH2CH3 branch. And we want to try all of these possibilities. And we're going to repeat this process, continuing to pull carbons off, continuing to move branches down the chains until all possible structures have been drawn. So we're going to look, for example, we're following again along with our worksheet, and we're going to draw the isomers. We're going to look at how we get those isomers for that C5H12. So we said the first thing we always do is we draw that straight chain structure. So we draw our 5 carbons connected in a row. So carbon 1, 2, 3, 4, and 5. Now when we're drawing that structure, so if we were just given that C5H12, we would draw our 5 carbons connected in a row, and then we're going to fill in our 12 hydrogens. And when we're filling in those hydrogens, we always want to make sure each carbon gets 4 bonds. So that's what distinguishes between getting a CH3 group on the end versus these CH2 groups in the middle. Again, we're just adding enough hydrogens so that carbon can get 4 bonds. It cannot have more than 4 bonds. So this would be our first isomer. Now the second thing we do, we said we're going to take a CH3 group off the end. So doesn't matter which end, we could pull one off. And then we're going to have to place it on an interior carbon. So if we were to take that off, that's going to drop us to a 4 carbon chain. So we would draw our 4 carbons, and we're going to place that branch on an interior carbon. So my interior would be one of these 2 carbons. So our next image here, this is what we have. We have even though this is folded a little bit differently, so you can draw these a variety of ways. You can draw them straight across. You can draw them, again, a variety of ways, because the bonds in reality bend, twist, fold, and rotate. So here what we're looking at is we have this 4-carbon chain. So again, we could have drawn that straight across. We could have just done 4 carbons. It's going to be the same structure. What we're looking at here is now having a branch on carbon 2. So that CH3 group we pulled off of the end, we have placed it on this 2nd carbon. And then we would fill in our hydrogens. Now, this structure I've just drawn and the structure that we see in this image, they are the same structure. So we said one of the ways of figuring out if we're drawing same structures or different structures is to count those carbons. So we have to count our longest continuous chain. That is not always straight across. So here the longest chain is actually that block of 4 carbons. We know it is the same structure as the one I just drew because the branch is on carbon 2. So I have a 4-carbon chain with a branch on carbon 2. Now, for this particular structure, we could move it. So we said the next step would be to move that carbon to the next carbon in the chain. So if I had my 4-carbon chain, so we started on the 1st carbon from the left, we're going to move over and we're going to put it on the next carbon. Now when we count our chains, remember we count from the end closest to the branch. So in that first structure I drew, the branch was closest to the left, but this time the branch is closest to the right. So now we're going to start numbering from right to left. I've moved my branch to that other carbon, but it's not a new structure. It's actually my original structure just flipped over. So again, if you think about it, if you turn around, so my molecule can turn around. If you turn around, you're not suddenly a new person. My molecule flips over. It's not a new molecule. It's the same structure. We can just look at it from different angles. So here, the branch is on carbon 2. My other structure, the branch was on carbon 2. This is not a new isomer. It's a valid structure. If you were asked for the isomer, you could draw it that way, and that would count. It's just not a new structure. Now, our next step would be to continue to pull branches off. So what we would do in our next stage, if we pulled another branch off, we would drop to a 3-carbon chain. And I would have to have 2 carbons in branches. I only have 1 interior carbon, so I could put my branch here and my branch here. And that would give me my other isomer that we already saw for our C5H12. Now we're going to walk through another example. We want to take a look at drawing all possible isomers for C6H14. So again, we're always going to start with the straight chain structure first. And you can draw this however you feel comfortable. You can draw your 6 carbons connected in a row using your expanded structure. And then fill in our hydrogens. Making sure we have 6 carbons and 14 hydrogens. You could also have drawn this as a condensed formula. So remember, this is our expanded. Or we could draw this as a line structure. So if I have 6 carbons, We want to make sure that our line formula has 6 points. So this would be my line formula. We could draw either. So that is always going to be our first isomer, our straight chain structure. Then we're going to take a branch off of the end. So if I take a branch off the end, we're going to drop to a 5-carbon chain with 1-carbon branch. So I can draw my 5 carbons connected in a row. I need to place my branch on an interior carbon. I have 3 options. I cannot place it on the ends. It can only be on an interior carbon. So I'm just going to use my first interior carbon. And I'm going to fill in my hydrogens. I'm just going to do the condensed just so we can get through this quickly. So this is now my second isomer. If I were to draw my line structure, we're going to draw our zigzag with 5 points, and then we're going to have our branch coming off of carbon number 2. Now, our next step is we're going to move the branch down the chain. So we're going to go with another 5-carbon chain. We're going to move our branch to the next carbon. So I'm going to place my branch on that second interior carbon. Again, I've got a number. So along my 5-carbon chain, this is indicating my carbon is on branch 3. So it's on a different, or it's on carbon 3. It's a different carbon. This is a new isomer. So this is my third isomer. I'm going to fill in my hydrogens, again making sure that each carbon has 4 bonds. And I could draw my line structure. So I'd have a zigzag with 5 points with my branch coming off of carbon 3. Now, we would go ahead and move that branch to the next carbon. So I draw my 5 carbons connected in a row. I place my branch here. But remember, we've got a number. And we have to number from the end closest to the branch. So this time that branch is closest to the right side, so I'm going to number from the right. That puts my carbon on number 2. This is not a new isomer. It's not a new structure. It is the same as the isomer I already drew for isomer number 2. So what that means is I have tried my branch on all 3 of my interior carbons. So that is as many structures as I can draw with this 5-carbon chain and a 1-carbon branch. So then my next step is to pull another branch off, and we're going to drop to a 4-carbon chain with 2 carbons in the branches. And 2 carbons in the branches could be 2 CH3s or CH2, CH3. And we're going to try all possibilities. So I'm going to drop to my 4-carbon chain, my 4 carbons connected in a row. And I'm going to start with my 2 CH3s. Now I have 2 interior carbons. When I go to place those branches, remember my carbon can form 4 bonds. So on my first carbon, I could put both branches on that carbon, or I could put both branches on different carbons. If I put both branches here, that gives my carbon 4 bonds, and I can fill in my hydrogens. This is now a new structure. This is my 4th isomer. And in this structure, we've got 2 branches on carbon 2. Now, just like we did with one branch, we've got to move those branches all around. Now, if I draw my line structure, I'm going to have 4 points with 2 branches coming off of carbon 2. So again, my 4 carbon chain, we're going to move our branches. If I put both branches on that next carbon and I number, that still puts my branches on location 2. This is not a new structure. So there's only 2 interior carbons. I can only move those branches together, or I can only put them together in one structure. But I can also separate them. So we could draw a structure like this, where they are on 2 different carbons. So I have a branch on carbon 2 and a branch on carbon 3. This is now a new structure. This is my 5th isomer. Now, there's nowhere else to move these branches. So the other option we would try is having that CH2CH3 branch. So I would have my 4 carbons, and then I would have a branch with a CH2CH3. Here again is where it becomes very important to count our carbons. So if I counted straight across, that would be 4 carbons. But we want to find our longest continuous chain. And that may not always be straight across. We have to check through what looks like our branches. And if I go through what looks like my branches, I have 1, 2, 3, 4, 5 carbons. This is my longest continuous chain. And this would have a branch on carbon 3. This is the same as isomer number 3. So it's not a new structure. I could move that CH2CH3 group to the next carbon, but it's going to give me the exact same thing. There are no new structures I can draw with that CH2CH3 branch. So then we would drop to our next lowest chain. So we could drop to a 3 carbon chain. If we had a 3 carbon chain, we would have to have 3 carbons in the branches. If I drew my 3 carbons straight across, there's only 1 interior carbon. I cannot put 3 carbons on 1 carbon. So I cannot draw any structures with that 3 carbon chain. So at this point, we have drawn as many possible structures as we can with the C6H14. You guys will have some practice problems. We'll do some additional practice in class. You'll also have some additional practice in your resource folder along with answer keys. Drawing isomers is just going to be a lot of practice. It's kind of like solving a puzzle. You've got to look at every different angle. Now, in our next video, we're going to pick up talking about naming compounds, because when we talk about our isomers, if they're different structures, different compounds, they need to have different names. And naming our structures is another way that also can help us determine if we've drawn the same structure or not.